Hello, everyone. Thank you for joining us today for the latest in the Dare Hub webinar series. I'm Dr. Ning, and I'm a research associate at the University of Cambridge and serve as the Work Package 3 coordinator for the Dare project, which is the UK's national research hub for decarbonized, adaptable, and resilient transport infrastructures. For those of you who may not be familiar with DARE brings together academic researchers and UK transport stakeholders, including national and local government, industry, civic partners, and transport infrastructure owners and operators, and to explore the viable pathways and solutions for a transition to a resilient and net zero transport system. Our hub is funded by UKRI, EPSRC, and the Department for Transport, and involves a collaborative team of researchers from Newcastle, Glasgow, Harvard, Anglia Ruskin, and Cambridge universities. So in today's webinar, we will be discussing smarter lifecycle maintenance planning. As in many economies, transport networks are aging while demand continues to rise. And at the same time, climate change is intensifying both the frequency and severity of extreme weather events. These combined pressures make it increasingly challenging to sustain infrastructure performance with constrained resources. So addressing these challenges requires more intelligent and forward-looking maintenance strategies, within which lifecycle modeling and emerging technologies are becoming central enablers of this transition. So this session will explore how lifecycle insights can help deliver smarter maintenance planning by turning data into better decisions, from understanding long-term performance under changing environmental conditions to detecting early signs of deterioration and leveraging data to optimize interventions that deliver the greatest value. So we are going to hear from two speakers and have time for a Q&A session after each presentation. So if you have any questions, please feel free to put in the chat at any time or raise your hand after the presentation to ask the questions. Now, let me introduce our first speaker, Professor Mahesh Pandey from the Department of Civil and Environmental Engineering at the University of Waterloo. Professor Pandey is a distinguished researcher with over 20 years of experience in probabilistic safety assessment and life cycle management of infrastructure systems. He leads an extensive research program funded by Canada's nuclear industry and the Science and Engineering Research Council. Professor Pandey has co-authored more than 300 peer-reviewed research papers and served as a co-editor for the Journal of Reliability, Engineering, and System Safety. He will present a probabilistic framework for evaluating the impact of climate change on the safety of Earth's embankments, widely used in transport infrastructure. It will also demonstrate that a non-stationary stochastic process can effectively model extreme precipitation in the future climate under a high emission scenario. So with that, I would like now to hand over to Professor Mahesh Pandey. Thank you very much, Mahesh.
Thank you. Good morning, all, and let me begin sharing my presentation. Good morning. Thank you for introduction, Ning, and I thank you all for this opportunity for sharing some of my ongoing research at the University of Waterloo, and is focusing on the life cycle management of a wide-ranging infrastructure system. So, general objective in civil engineering, as always, is ensuring safety and performance. Performance could be cost or managing the functionality of the system over the life cycle. And we're looking the public infrastructure system, which includes building and transportation, water, waste, and power generation and transmission system. So our research program in Waterloo is more focused on integration of, you can say, risk and reliability metrics with life cycle assessment. And in the process, we need to consider the temporal changes in the demand and capacity of the system. How do we account for uncertainty over a long service life of these systems? And probabilistic models supported by data are integral part of these modeling. So we all know this. There's nothing new about this. Data is always, as you know, in any assessment when we have a probability statistics is important element. both in the design stage and maintenance stage. We use these probabilistic models and methods which are calibrated by real life data. So two steps are there in the initial design, setting the requirements for initial design, developing codes and standards. We use a reliability based method, which are very common in civil engineering systems of all sorts now. And we need data regarding the service loads and material properties and interactions and so on and so forth. More importantly, in the long life infrastructure system, we also look at now the vulnerability to degradation processes. What can go wrong over the lifetime. Condition monitoring provides the data. So how do we synthesize this data in the assessment and support the inspection maintenance planning decision. And the life cycle cost optimization is also a very we can say conventional tool nowadays to find the right strategy. So in summary, what I wish to say is that probabilistic modeling and statistical methods are natural tools for dealing with this problem of safety and functionality of infrastructure system. Uh, and I always remind the researchers and the user that it's an information intensive process. I mean, it's not that we can do in a casual sense. So a basis for any, you can say, the skeleton or the backbone of a life cycle assessment, at least the kind of research we do, is a stochastic reliability analysis model. And what I thought is just give you a conceptual flavor of it. The time is limited to go into all the details. So what we are approaching this problem as by modeling the load events and degradation in the capacity as stochastic processes. So this allows us to include the temporal uncertainty. So what you see on the x-axis is essentially a time horizon or service life of the system, and the y-axis is both load and strength. And load events, you could see, is kind of a point in time, of random magnitude. These events are arriving and challenging the capacity of the structure. And on occasions, these loads could increase, demand could increase the capacity, and then these interactions basically would lead to so-called damage and failure events. And we want to estimate the expected losses resulting from these events, so to speak. And once we have a better idea, and these, of course, these models are calibrated with the available data and expert assessment. Once that we say at the baseline, then we could approach to optimize inspection and maintenance as a way to mitigate. So in summary, basically, I need this type of model or this type of analysis which gives me a probability of failure over time for different modes of failures. It's not for single mode, different modes, different limit states, so to speak. So this is kind of the basic schematic of the method here. Then the angle that I wish to present here is in the research is on the climate change. And that is the concern also in Canada, where the climate change is at a accelerated pace as compared to rest of the world. And these changes are evident now by increasing frequency and intensity of extremes. It's a common headline nowadays in the newspaper and media. You hear about record-breaking heat waves in Canada now, rain and snowstorms and hurricanes and atmospheric river. And of course, all these events are challenging the infrastructure safety and functionality. And in the front line, you have the transportation system, electrical networks, water infrastructure, and we hear the news about these systems are frequently damaged and disrupted. So as a technical point, as an engineer, what we make a note is that the climate change is causing temporal variations in frequency and intensity of weather extremes, and the sustained global warming will continue to sort of amplify these effects. So key research gap is the non-stationarity. All the existing design codes and standards implicitly assume that we're dealing with the stationary climate. So all the load models that we use are essentially stationary processes. So research gap that we identified is the non-stationary models are needed for evaluating reliability of infrastructure system, and that work should also be able to support revising the design codes. So this is the kind of the angle that we are pursuing the research in Waterloo at the moment. So just a slide to show more visuals about British Columbia in 2021 has a major rain and flooding caused by atmospheric river event, extreme event. And as you could see, the earthwork is always at the front line when it comes to transportation system. So damages to roadways, and you can say railway track here, the landslide basically took out all the support for a railway track. And more importantly, we saw in case of bridges, the bridge approaches were very vulnerable. Either they just had a slope instability, landslide, washout, discovering, all sorts of phenomena were happening because in the gush of water. So bridge superstructure was standing perfectly fine, but just approach was not available, and that made it unusable for long period of time. So safety of infrastructure system is what we are focusing on, and also a bit of inspiration from my attending last DARE seminar where discussion was on the earthwork. We begin to look at, okay, how the climate change will affect the earthwork in the transportation system. How do we bring climate change effect into modeling? And this is also interest now in Canada, especially after the larger scale destruction we saw during the British Columbia flooding event. Naturally, climate change has a two most dominant effect, most visible effect is in the temperature, heat, and precipitation, water. So either we have too much of these things or too little. So question is now how changes in precipitation pattern will impact the frequency of slope instability and landslide. Uh, and because we know these slopes, these events are very, very disruptive. So needless to say, justification is there to look into these research. So what I have done in this seminar, I'm just presenting more conceptual approach. I thought that would be worthwhile discussing, debating, as opposed to going into all numerical details. So what we have thought of is a kind of an integrated approach in which we look at the climate change module, you can say, climate change processes, how they feed into the reliability of a system, you could say, based on the mechanistic model of failure. And of course, then we look at the time dependent changes through modeling degradation processes. And all these three elements then feed into life cycle, you can say, risk analysis or cost analysis, which will follow at a later date. So we started a pilot research project because to have a buy-in from stakeholders, we want to demonstrate that we can logically integrate all these modules together and provide some meaningful answer, which are of practical use. Otherwise, as you know, we academics are always accused of doing a lot of textbook stuff, which may or may not have limited practical application. So this is sort of is the intent of the ongoing project, and I wish to share some of the thoughts and ideas and where we are. So this is work in progress. So integration of multiple model, how we would go about it is this is what the objective is, and in the end, our thinking is that well, this integrated risk assessment will provide basis for mitigation and adaptation measures by our National Research Council and Infrastructure Canada and other agencies. So as a demonstration example, we started working on the earth slope instability analysis model. And first we thought, okay, let's start with a simple mechanistic model, which we can solve analytically and integrate all the elements together, demonstrate the feasibility, and then work with more complex issue. So of course, the first issue is always the modeling of the climate change effect, especially on the precipitation. So what we have done is we looked at the ensemble of 26 global climate model coming from the latest phase year. So the first plot that you see is the projection forecast from 2020 to 2100 of the annual maximum precipitation. It's basically daily amount in Toronto, Ontario. So just as an example. So you could see the data, these GCM model have a lot of noise, a lot of uncertainty, so-called the internal variability or chaotic variability of the model, as well as the model uncertainty, and many other factors that contribute to it. So how do we capture this uncertainty by more, you can say, concise, parsimonious a model, and that's where the probabilistic analysis helps. So we could basically use a non-stationary gumball model to begin with. That's a simple model. and now we have a representation of all the uncertainty in the model, and this could now be input to the analysis. So we also looked at the work on the non-stationary shock processes, where we have more control on modeling the frequency and intensity of processes as a separate element. And a lot of work we have done here using the non-homogeneous Poisson process, and also looking at the non-homogeneous birth processes called the linear extension of fuel process. So stochastic modeling of practical problem is our sort of a niche expertise. So we spend a lot of time doing these things. The non-stationary components are both frequency and intensity, and we can also include the dependence. But the nice thing is the final output is essentially a distribution of maximum precipitation in any given time interval. These distribution and analytics is manageable. We can get in a more analytical form, which makes it easy to do subsequent simulation and all those things. So here is the results for the NHPP and then LEYP model, and I won't go into detail. All the publications are there, reference at the end of the presentation that you can refer to. So now coming back to the Earth slope instability problem, what we have done is really have a probabilistic version of this infinite slope limit equilibrium method, standard model you can say in the geotechnical engineering. Look at the more Coulomb shear strength model, and what we do is calculate the factor of safety during the rainfall. So on the right hand side you will see the rainfall event of 50-hour long, for example, and we knew the total cumulative rainfall I think is about 120 millimeter or so, and this is the pattern during that event, and the dark line that you see is the calculation of factor of safety of the slope, which becomes less than 1, which means slope becomes unstable for this pattern of rainfall, and that leads to failure. So rainfall infiltration is also right now the simple model I said just for illustration purposes. So what this model does, it gives us the computation, it gives a conditional probability of failure for a given total rainfall. So by varying the amount of total rainfall, we can calculate essentially a conditional probability curve that is called the fragility function. So there's also in terms of the how do we use this in a practical sense, we face a kind of another research problem to be addressed, and the problem is that for slope stability analysis I need high resolution rainfall data, hourly basis rainfall pattern or maybe even less. And naturally when we look at the climate simulation data that are available, they are not at such a high resolution. At best we can get is the daily basis resolution. So question is then how do we connect the two? If I just use the daily basis data, we will not be producing a correct result for the slope instability analysis. So that becomes a kind of a research problem. How do we reduce or convert low resolution data and infer a high resolution rainfall pattern from it? So there are two, at least in a stochastic world, two possible solutions. We can look at the clustered Poisson process model, and second is the breakdown coefficient method. So we have used the breakdown coefficient method, and again we have done quite a bit of work just completed now, where the idea is that we look at the total rainfall over a given duration and randomly split into different time slices. It's also called the beta distribution splitting, and this is based on the idea of what we call the self similarity, statistical self similarity in the fine temporal scale and the larger temporal scale. So again that method seems to be working effectively. So here is just putting it all together, as the time is running fast. What we will have is a fragility function curve. This is just an illustration, not a real calculation. So first thing we will have is a fragility function, which will come from the slope stability analysis, breakdown coefficient model, and all those things integrated here. We combine this with the extreme precipitation distribution. Second element comes from the climate change model that we have through stochastic process model. Combining the two will give us the final so-called probability of failure curve over future time horizon, over the life cycle. So we will have this kind of calculation done for some kind of a base case situation, and we can look at the second curve for the some future emission scenario, and that would give us the measure of incremental risk. So this is sort of where we are at. We have completed all this modeling work and just running the calculation and example right now. So I apologize not being able to present more realistic example, but this is where we are at. Last piece of element would be degradation modeling. Again, the challenge is, the earth slope especially have a wide ranging degradation processes, and mechanistic modeling tends to be complex and uncertain. So we'll have to see how do we manage those challenges. In terms of stochastic modeling is always feasible at high level. We can look at the Markov chain, discrete condition state. So right now the project we have is looking into a non-stationary Markov chain model of degradation. Uh, and we are focusing on the time transformation method, again, which is a more concise and parsimonious way to convert an existing Markov chain into non-stationary model. And this way we can use the currently available chain model. And this is we are applying to the bridge condition rating system that our transportation agency is using. So this brings to me to conclusion of this overview of ongoing research in Waterloo. Non-stationary model nature of climate change is expected to intensify. This is sort of the basic premise. And we are looking into safety of Earth embankment model as a pilot research project and apply all these stochastic life cycle research and analysis methods. We have a number of elements in the research program, looking at the modeling of extreme precipitation or another extreme process, probabilistic analysis of the system under concern. So here we are looking the slope instability problem, and I think the fragility function to me is a sort of as a proposal which comes from the seismic risk analysis world, is a convenient way to integrate all these effects together. And in the terms of path forward, we are just getting into now more detailed models of embankment failure. What I presented is a very simplistic view. As you know, there are many other methods and mechanisms that need to be considered. And more importantly, our students are now starting to work on practical application to earthwork examples in transportation system in Canada. And I hope to report those results in the coming days. So thank you for your attention, and I hope I'm in reasonably in time. Thank you.
Many thanks, Mahesh. Very great presentation. So if you have any questions, please feel free to unmute and go ahead to ask or put them in the chat. See, now we have some questions in the chat from Christian about what data have been used for modeling the level of precipitation to 2100.
So basically what we have done is, sorry, yeah. Yeah. So what we have is the so-called global climate model. It's a suite of models under the coupled model interaction project. So worldwide meteorological agencies, you can say, they have these climate projection model, which they run all over the globe. So we have a selection of 26 model for Canadian geography, you can say. And I look at those forecast data for city of Toronto at the moment.
And please, this model is based on data over how many years? 5,
So,
10, 100, 200 years?
It's
So
it's a 100 it's a 100 year of the forecast. So we have looked at the
no,
18.
not how many years from now on. I mean, the data being used for the model are probably using data collected over the past period. And this past period is how long? 10
No,
years,
that no,
5
sorry,
years?
sorry. No, no. The climate model forecasting is done for the future climate. These are based on the climate science model, global circulation model, so to speak. And what they do, they calibrate these models from the past data, typically from 1900, whatever available, to the 2000. So they will calibrate the model for last 50, 60 years of data. And then after calibration, they do the forecast of the future climate for next 100 years. So we are using the models that are calibrated for Canadian data, for example, by Environmental Science Canada Department, and they provide the projection for the next 100 years.
Yes, thank you.
So great. Let's move on to the second questions from Difei. Which impacts of climate change have been taken into account, and do different impacts of climate change exhibit variation? How are they represented in the model?
Yeah. So basically, what we are looking right now is mainly the high emission scenario, what they call the socio-economic pathways, number 5. So it means the projected temperature change is 4.4 degrees centigrade in Canada by 2100. So it is the kind of the highest emission worst case scenario. So that's the data we have taken, and it's a daily time series of precipitation in city of Toronto, and we are looking at the purely the temporal uh, probabilistic structure, stochastic structure of the data set. And since we have 26 models, so idea is that we are covering the model uncertainty, fairly wide band of uncertainty, and the next 80 years of data basically captures all the impact of emission scenario, a high emission, whatever projected over the moisture content and precipitation and so on and so forth. So that is all the integrated representation of climate effect on one process.
Okay, great. And conscious of our time, our final questions from Tony. How safe is it to predict future short duration rainfall events from current patterns, intensity, duration, frequency, IDF curves?
There's always the issue, as I say. I mean, the resolution of these climate forecast um, are generally you have a 50 by 50, 50 kilometer by 50 kilometer grid, the GCM model. Then you have a lot of downscaling methods, which bring it down to more local scale, and all those uncertainties remain in this projection, and especially the short term, you can say, rainfall event. And as I say, even from daily resolution going into the hourly resolution, we are using our, again, probabilistic splitting of the data. So all those uncertainties are there. But the counter argument is that as a manager, as an engineer looking after infrastructure, we need to have some sense of the order of magnitude of changes that we can keep in mind so that we can plan for adaptation mitigation measures. So uncertainty would be there using different groups of models and different, climate science people are always, working and refining these models. So that challenges are there. I do acknowledge it. So my impression is that we will not get the so-called probability of failure in any exact sense, but it will give you the order of magnitude of the changes we are anticipating. And one example I give you, for example, in case of the wind load, we did the calibration of the wind load on structures. And when you look at all these climate models of all sorts and you find the projected change is will be about in the range of 5 to 7% increase in wind speed. And then we also find if that is the case, then it will have a very limited effect on structural reliability. So it gives you a sense of assurance that maybe in terms of revising design code, wind will not be a major contributing factor to safety of the system. So this is how sort of we are ballparking all these issues and trying to support the code committee to say, well, what could happen and how should we plan for them at this present stage.
Okay, great. Thank you once again, Mahesh, for this
Thank you,
great
Ning.
presentation.
Thank you very much.
Thank you. I believe we need to move on to our second speaker. And if someone else still have some questions, feel free to put it in the chat, and perhaps we can go back to it if we still have some time after our second section. So our second speaker is Dr. Difei Wu. Dr. Wu is an associate professor in the College of Transportation at Tongji University. He earned his PhD in transportation engineering from Tongji University and participated in a joint training program at the Georgia Institute of Technology in the United States. He serves as secretary member of World Transport Convention and committee member of the Chinese Society for Measurement and Control. His research focuses on digital perception, electrification and intelligent construction of transportation infrastructure. Dr. Wu has led more than 10 key research projects, including grants from the National Natural Science Foundation of China and the National Key R&D Program. He has published more than 70 papers in top-tier journals and holds over 20 authorized invention patents. So today, Dr. Wu will present a solution for managing China's extensive and aging road network. It will introduce a lightweight road performance evaluation system that uses sensors, AI, and 5G on standard vehicles to automate road inspections and detect distress with high accuracy. It will further demonstrate how digitalization enables a shift to data-driven maintenance using dense data and predictive models to optimize strategies and move from reactive repairs to proactive intelligent infrastructure management. So hand over to you, Dr. Difei. Thank you.
Okay, thank you. I'm going to share my presentation. Okay, thank you so much for the introduction, and also thanks for the invitation. And let me here to have this opportunity to share our recent studies. And before this presentation, I must thank Ning because she has contributed a lot to this study in the past 10 years. So today I'm going to share this presentation titled Digitalization Empowers Smart Management of Road Infrastructure. And from these four aspects, the first is background and the future trend in China. And we know that actually China is one of the countries with the highest traffic pressure in the world. And first, we can see some numbers for the infrastructure, especially road infrastructure. The population in China has already achieved more than 1.4 billion in 2022, and the highway mileage has already reached more than 100 kilometers, which ranks number one in the world. And over 99% of the highway are under maintenance. So it's a very huge asset for us to do the maintenance. And in the past 20 years, the mileage of the highway has become from 1.4 million kilometer to over 5.1 million kilometer. So in China, it has already been through a big transformation from the construction stage to the maintenance stage. Okay. So the maintenance of massive road assets faces huge challenges. We can see some cases. For example, in Shanghai, Shanghai is a very big and very old city in China. And in Shanghai, we can see the expressways. For Shanghai City Expressways, the longest service time has already more than 25 years. An average service time is over 25 years. And for the highway, the longest service time is over 35 years. All the road facilities, they are very old. They are getting older and older. And let's see the maintenance for these expressway and highways. And we have done lots of maintenance. And in 2015, one of the expressways was closed for 10 months to do the shock style maintenance. So that that influenced a lot for us for the transportation in Shanghai. So under this condition, we think that the limited data coverage and insufficient update frequency has become key factors restricting the high quality development of road maintenance and operation. So actually, the primary things for us is to capture data, especially road performance data. Actually, in the world, we have lots of technique and approaches to capture those data. For example, here shows the four typical detection equipment in the world, like the path runner, the road doctor, the road star, the iPave. They are a very big and high precise vehicle there. But all of these detection vehicles, although they have high precision, they can detect the road from multi dimensions, and it's automated, but they are all expensive. So actually, it's like for us human, it's just like to do the CT or MR examinations. So it's very high precision and very expensive. But for us to do the routine maintenance, actually we want to add more techniques, just like some thermometer, blood pressure meter, just like this lightweight and a cheap method to do the examination. So we think that road infrastructure also needs such techniques. So under this background, the first thing we do is we spend over 10 years to develop a lightweight road performance evaluation system. So the second part, I will introduce this system. Um, this system allows us to capture the data, capture the performance data from different aspects like the road roughness, anomalies, pavement distress, texture evaluation, and subsurface distress. And we do some 3D scanning to get the information of all the road facilities. So that's a lightweight system. And in this lightweight system, this system integrates cutting-edge sensing, AI, 5G communication, beta positioning, and other distributed technology to achieve digital oversight of the entire maintenance process. So here it shows this figure. This shows the scheme of us developed the system, and it has some modules there. We can see the cameras, the GPR module, the position module, and we have a edge computing server there to do the computation. And for some cases, we can apply some laser system to have a laser on the pavement surface, and we can identify the pavement deformation based on the shape of the laser. So that is a scheme of this lightweight road performance evaluation system. It's mounted on normal vehicles. And all the sensors can be assembled on demand, and the equipment operate fully automatically without human intervention. Almost any vehicle can be used as a detection vehicle. And then we can see this, here is a small videos here. So maybe it can have some time delay here. Here shows a video. We have this equipment just mounted on the top of the normal vehicle, and we have a camera there to capture the image of the road surface, and we also have some sensors mounted on the vehicle to capture the vibration data to get the pavement roughness information. So that's that video of this lightweight road performance evaluation system. Okay, so here now we go to the algorithms. So for the first algorithm is to inspect the pavement distresses, and for in this study we have proposed a road ID a road ID algorithm based on deep neural network to automatically identify the distresses and to quantify the size of each distresses, like we can see from the images. To develop this algorithm, we have marked more than 5 million training samples and over 1 million distresses detection cases. Yeah, and based on the edge computing technology, the data processing efficiency can reach more than 20 FPS, and the average accuracy can reach more than 90%. So that is a result after lots of training and developing. This is the final result.
Sorry to interrupt you, Difei. There might be some delays. We are still looking at the videos in your slides.
Okay, so I'm gonna stop this sharing first. I'm gonna move to the next slide. So can you see, I have already moved to the next slide.
Yes.
Can you see the next? Okay, so the former slide, we introduced some technology to detect the pavement distresses. And this slide, we also developed algorithm and technology to capture information of the curbs and walkway, especially in the city road. We have walkways and curbs. And in this scenario, we install these cameras on our bicycle or on our quadruped dog. It's a dog robot, and then we can capture the image of the curb and walkway. Then we identify these stresses. So that's a new technologies we have developed in the recent years. Okay, so yeah. So after we captured all the data, then we proposed a three-step spatial temporal matching and tracking algorithm that to monitor entire progression of the payment distresses. This algorithm allows us to track the deterioration of each payment distress over time. And this technique we have proposed is three-step. The first is to do the spatial location clustering based on the GPS information. And then we do the image background matching to identify if the two images are captured in the same location. And then we do the fine-grained feature matching based on the features of the distress itself. So it's a three-step matching algorithm. And based on this matching result, then we can review how the distress change or deteriorate over time, and then we can see some samples there. So see how the distress form from some small pothole to a big pothole, or from some very small one small pothole to lots of potholes there. So based on the dense data, based on the data we captured, then we can see how the distress formed over time. Okay, I will skip this. I will skip this slide. It's a video and may cause some time delay. So the former slide, we just introduced some technologies based on the image. And in this slide, actually, we have used vibration technology. We collect the vehicle suspension vibration information through distributed sensors, and then we establish the mathematical relationship between the suspension vibration and the pavement roughness index through PSD analysis. So we think that we have when the road is very rough, then that will cause a very huge vibration on the vehicle. So then we capture the vibration information of the vehicle. Then we can we can then evaluate the pavement roughness level based on the vibration data. So that's the core technique we have studied in the past 10 years. And we know that for the payment surface, we should not only focus on the surface distresses like a crack or potholes. We should also focus on some deformation like rotting, raveling, just some deformation distress. But actually, this type of distress is very difficult to measure or to detect. In traditional ways, the researchers use some laser use some LiDAR technologies or laser technology to measure the distance between to detect the profile of the pavement surface, but they are expensive. So in our system, we use the low-cost rapid detection method that we have a laser just scan laser just on the pavement, and we can see the green line here. And if the pavement surface is very flat, then that will be a straight line. But actually, we can see it's a curved line. So the shape of the laser that we can um, we can identify the deformation position based on the shape of this laser stripe. So that is a lightweight technique to measure the pavement deformation. Okay, um, so the former slide we introduced some technologies to detect the surface distresses. And this we also develop a system that combined with we utilize the GPR, the ground penetrating radar, to capture the subsurface information to detect the subsurface distresses like poor bonding, settlement, cavity, crack, when water reach just under the pavement. It is also a very it is also very important for us to do the maintenance. And this technique is based on the LiDAR technologies. We use the LiDAR technology to capture the 3D geometry of the road environment. So I will skip this. So, okay. So that is the result. That result, we can get the 3D information, 3D geometry information of the road and beside the facilities, and also the lines and the traffic signs on the pavement. So, but this technique is very expensive and a very high precision. So I will skip this. So based on the data we captured, then I'm going to show some interesting findings based on the dense data. So I'll skip this. Okay, so let's see some interesting findings based on the captured data. So first, we can see the first case. We can see some frequent distresses. Based on the data, we find just one. For example, here we have a pothole. In the first day, it's a repaired pothole, and after like 10 days, we can see some minor damage. And then after 2 days, it becomes a pothole here, and then the pothole intensification. And then after about 10 days, it becomes a very severe pothole here. So based on the dense data, we can see how the distress formed over time. And this is another case is here. It's a repaired pothole. And just after 6 days later, then the pothole becomes a very severe pothole. This repaired pothole becomes a very severe pothole. It's a pothole formation. And then just after maybe 10 days, it's repaired again. But then after 2 weeks, it becomes another, it also, the pothole formed again. So that based on data, we can show how the maintenance and show how the traffic influence this distress. And this is a cases for the joint damage. I can see the bridge joint here is intact, and then the minor crack occurs, the pothole formation, pothole intensification. And this we can also evaluate the some climate change, influence of climate change. Here is cases of the shows the impact of the typhoon. And before the typhoon arriving here, we can see some repaired pothole here. And just after the typhoon, then the lots of pothole just formed. And this is before typhoon arriving and after this typhoon. So we can see that the climate change and the typhoon, the severe climate, have a very big influence on the pavement performance. And this, I'm going to show one case due to the time limit. So in this case, we can see first we get the maintenance record, and then we find that in this place, this pothole repaired again and again and again. Just maybe in about 2 months, it repaired more than 5 times. So we think that maybe the core causes is not because of the pavement surface. So then we use the GPR system. We use the GPR technology to detect the subsurface condition. Then we find that the major causes of these surface distress is made due to the subsurface condition, due to the subsurface defects. So then this shows the GPR result shows uneven subsidence here. So that's the main causes of these pavement distresses, of this pavement surface deterioration. And this is another cases here. And also based on the lightweight detection system, we combine the vibration data and the image data. And then based on the two data, we can we can monitor and we can detect the bridge joint here, detect the performance of bridge joint. So first, based on the image data, we detect the bridge joint. and then we just capture the vibration information of the corresponding time, and then we can evaluate the spring joint, the height differences at the spring joint based on the vibration data. So that is uh, a combination of the vibration sensing and image detection. Okay, so here we also I'm going to show some more interesting findings here. So in Shanghai, Shanghai is this very big city. In this very big road network, we captured all the data of the road network. Then we can see the distribution of the pavement performance. Then based on distribution, we can see what's the causes of this of some severe region here. And so we can see here these are development zones, logistic hubs, and this location may they are the main causes of how uh, to um, to explain why this region deteriorates the most. And then here, this is a downtown region in Shanghai, and we can see the construction zones, the old urban areas. They, this region, the payment performance deteriorated the most. And this is another distribution of one district in Shanghai. And based on the distribution result, we can it can help us to do the maintenance decision making. And based on data, we also developed a agent based on the generative AI. And due to time limits, I'm gonna skip this. So because I already take more than 20 minutes to share this presentation. So I will skip this. So these some cases with the generative AI based on the captured data. We use some large language model to help us to do some decision making, to help us to give us answers, help us to do the maintenance, to give us some advices. So I will skip this. So here is the conclusion, and the first we have the past with the studies we have done in the past 10 years, we have transformed the data capture modes in China from the sparse data to dense data. And also, we have transformation of the maintenance models from sampling inspections to high frequency modeling, from small models to large models. And then for the digitalization of infrastructure, we just transformed from accuracy oriented to function oriented. So that's the main conclusion of this study. So thank you. Sorry for that I have used more than 20 minutes to share this presentation. Okay.
No worries. Thank you, Difei. And we can see here are some questions in our chat from Kristen about the GPR data. First one, according to your experience and work done, which is effectively the max depth for collecting reliable data? And the second question is, how is the interpretation of realized data done, bearing in mind the different substructure, designs, materials used, etc.? How are the abnormal features detected versus the normal ones, which show differently due to the different layers, material, etc.?
Okay, so it's a um, very interesting question. So for the first question, you mentioned that about GPR data, especially the max depths and collecting reliable data. Actually, it's a very hard for us because the depths, the detection depths that is that related to the uh, region you are in, and that is related to the soil type. For example, in Shanghai, Shanghai is a city just near the ocean, so the water level is very high. So maybe we can only detect the like 2 to 3 meter depths. So that's the max depth in Shanghai. And maybe in some some west region in China, the water is very dry. In this region, the max depths can reach more than 5 meters in this region. So that depends on the water content in the soil. So that's the core factor. And the second question, let me see how is the interpretation of visualized down bearing in mind. So it's also about GPR data. So actually, we know that GPR data is actually for us, from our experiences, the first step is very difficult. It's very difficult for us to mark the abnormals from the raw data. You must have lots of experts there to read the raw data and to mark the abnormal features. And and for now, so we have already collected like over 4,000 samples, and for each samples we have we have a small camera just inject in this region to get the real data. So for each samples we get the GPR raw data, and we also use some camera. The camera, we can inject the camera in the payment in into the subgrade and to see if it's a void, a cavity, or some abnormal deformation. So then that is the true data. That is the real data. So based on the marked GPR raw data and choose data, then we can develop some algorithm to automatically detect those uh, abnormal features or to detect some distresses under the pavement surface. So actually, that is still lots of problems regarding the GPR analyzing and use the GPR data to identify the distresses. So actually, it's for the GPR we have still working on how to process the GPR data. Okay.
Great, thank you. Any more questions? If there is not, I do have questions regarding the decision-making process that you might have mentioned last. After you gathered all these data and information, how would you integrate all these data for your decision makings? And for example, if you have different formats of data and the different levels of the precipitation result, how you combine all of them to make your decisions?
Uh, yeah, it's a very interesting question. Actually, about 2 years ago, it's a very difficult task for us to combine all the data with different modes. We have vibrant data, we have image data, we have some text data. So it's very difficult for us to combine all the data, to fuse all the data to help us to do the decision making. But fortunately, now we have the generative AI tools. We have large language model. So then we can just put every data just in one large language model and let the large language model to understand the meaning, to understand what's inside, understand the feature of the data. Then based on the understanding results, so what we have the only thing we have to do is to deal with to process the result data based on the from the large language model or some generative AI tools. So for now, so in this year, the one of the very one of the study we have done is to how to use the generative AI, how to use the large language model to deal with the historical data. Most of the historical data are text data. So they are in the books, they are in the papers, they are reports. So first we just translate this text data to the digital data based on the large language model. And then we just combine all the monitoring data, the detection data, and then we use large language model also to process this data. Then The only thing we do is to deal with the results from the large language model. So it becomes more convenient and more simple. So actually, that's what we are doing in this year.
Great, thank you very much. So thanks to the emerging technologies, we can solve some tough issue that we cannot solve
Yes,
before.
yes.
So yeah, that's a really good idea and news. Thank you very much again. I believe that we
Thank
need
you.
to wrap up now, and I believe our speakers would be happy to follow up with other questions after the webinar. So thank you once again, Professor Mahesh Pandey and Dr. Difei Wu. Thank you both for the great presentation today, and thank you for giving up your morning time and evening time to attend this. And also thank for all our audience for giving up the lunch time to come and attend the webinar. We hope that you find today's session insightful and that they have provided valuable perspectives on how life cycle insights can help support smarter maintenance planning. And hope you all have a great day.